requires it 0 minus to infinity f prime of t e to the minus t dt. Okay? So this is, if I call this g of t, okay, this will be g hat of x. This is a Laplace transform of the derivative of this. But then if I call gc of t to be this thing over here, this thing now has two terms. It has this area in addition to the other function. So if I were to find the Laplace transform of this, I would have 0 minus infinity, okay, something that exactly looks like f prime of t, okay, something that exactly looks like f prime of t, but then you have an additional term, which is the delta function term. The delta function term has the height of f of 0 right at that point, okay, f of 0, and then plus the rest of fc prime of t just looks exactly like f prime of t. Okay, this part looks exactly like this part over here. Okay, so if you work this out now, it's f of 0, okay, plus 0 minus to infinity f prime of t e to the minus st dt. Okay, and then you find that this is equal to f of 0 plus g hat of s. Okay, hence you have the relationship. Let me put the relationship up here in this top right hand corner, that g hat of s is equal to gc hat of s minus f of 0. Okay, this means the Laplace transform of the causal function. Okay, that's why you have this kind of relationship. Okay. So you can go on and on. So if this is true for the first derivative, what should be the Laplace transform of the second derivative? Say if we apply this rule over and over again. Okay. If f prime of t Fourier transform to that, f double prime of t would Laplace transform to s times the Laplace transform of f prime of t, which is s minus f of 0 minus. Okay? And then minus f prime of 0. Actually, it doesn't matter whether put 0 or 0 minus. As you can see from the derivation, it doesn't matter as long as that function is clearly defined over there. So if you apply this rule once, you get this being equal to s squared f hat of s minus s f of 0 minus f prime of 0 minus. Okay, this is f double prime of t, f double prime of t, Laplace transform to that. Okay, so the general rule is that if you have the n derivative, then you know what to do. N derivative of t will Laplace transform to Sn f prime of s. There is a formula. Okay, let me just copy the formula from the textbook, which is just obtained by repeated application of this. Okay, minus dot 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 s f of n minus 2, 0 minus f of n minus 1, 0 minus. You just apply that formula repeatedly, then that is true. But if it's causal, if a function is causal, if f of t is causal, like this function over here. Okay, if f of t is causal, then this always evaluates to 0 by the definition of causality, and all this will evaluate to 0. Okay, then f of n derivative of t, Fourier Laplace transform to Sn f of s. Okay, that's simple. You can drop all the f of 0 terms. Okay, and you understand why. And of course, there's this convolution property that I derived before, but I hope I don't have to derive it again, which is that if y of t equals to f of t convolving with h of t, then y of s is equal to what? Is f of s times h of s. Okay? The property that I derived before, but I hope I don't have to derive that again. Okay, and then there were some examples, example 11-14, that makes use of this convolution property. And this convolution property is derived based on causality. Linear time invariant causal system. If the system is not causal, this derivation does not go through. Okay? So if you have something that's non-causal, do not use this convolution property. Okay? And I can derive this property again maybe, since I have 5 minutes left. You can see where causality comes in. Okay, I can find the Laplace transform of the left-hand side will be equal to 0 to infinity dt y of t e to the minus st. And then, because it's causal, because this is causal, if the input is causal, this must be causal. If it's causal, it is only non-zero for t larger than 0 minus. So I can always make this integration that way. Okay, then I can plug this integration for convolution in there. E to the minus st. And then I write this as a convolution integral. dt 0 minus to infinity. And then writing the inner integral as a convolution. Okay, it would be tau, h of tau, f of t minus tau, the tau, and then tau goes from 0 minus to infinity because this is a causal function. Okay, and then e to the minus st is what I should have. And now I can actually do the dt integration first. I change the order of integration and do the dt integration first. Do the d tau integration later. Okay, left the d tau integration on the outside. And then do the dt integration first. And the dt integration is just a Laplace transform integration. Okay? I can either do this by a change of variables, or I can use the time delay property of Laplace transform, given that tau is larger than 0. If f of t Laplace transform to f hat of s, what does f of t minus tau Laplace transform to? We just learned that. No, that is the derivative property, the time delay property. E to the minus s tau f of s, right? So I can use that, I can do a change of variables. So what I have left is actually f hat of s times 0 to infinity d tau h of tau e to the minus s tau. And this is just equal to h of s. And hence I have this property proved. Okay? Is this clear? So that is the convolutional property of Laplace transform, almost like that of Fourier transform, except that you have to make sure that the signals are causal. If the signals are not causal, the derivation does not go through. Okay? And there was an example of 11.15 where you were asked to convolve two non-causal functions, and then the answer is no, you cannot apply this property. Okay? And then there are other examples in the textbook that you can go through. I guess I'll let you go since you only have 1 minute left.